If you strip away every molecule of air in a room, creating a perfect vacuum, you lose something else entirely. Take the classic bell jar experiment. Inside the glass, an electric bell is clanging away at full speed. But because a vacuum pump has sucked all the air out of the jar, there is absolute silence. Sound is a mechanical wave, requiring a material medium, like a gas, a liquid, or a solid, to physically propagate. Sound relies entirely on a physical chain reaction of matter colliding with other matter. If you remove those molecules, the kinetic energy simply has nowhere to go. When an object vibrates, it pushes the surrounding air particles forward. This forces those particles into tight, high-pressure clusters, which physicists call compressions. As the vibrating object snaps back, it leaves behind an area of low pressure, known as a rarefaction. Individual air particles bump into their neighbors and return to rest, staying relatively localized. The kinetic disturbance is the only thing that travels across the room, but this presents a fascinating biological problem. We walk around in a sea of thin, compressible air. Our brain, however, is locked inside a thick vault of solid bone, floating in a pool of fluid. So how does an invisible ripple of air pressure cross that dense barrier without losing its energy? This anatomical diagram shows exactly how our body solves that problem, starting with the outer ear. The visible cartilage on the side of your head, called the pinna, acts as a biological antenna to catch those waves. Its specific folds funnel the alternating bands of high and low pressure inward. The wave is then forced down the ear canal, a narrow, wax-protected tunnel. By the time the wave reaches the end of that tunnel, a wide, diffuse wall of atmospheric energy has been successfully captured and concentrated into a single point of impact. At the end of the canal, that concentrated wave crashes into your eardrum, vibration. Taking a closer look at this inset diagram of the middle ear, we see what happens next. The vibrating eardrum triggers a sequence inside the body's three smallest bones, the hammer, the anvil, and the stirrup. Sitting in an air-filled chamber, these interconnected ossicles act as a mechanical amplifier. They use physical leverage to multiply the force of the incoming vibration. Without this tiny, solid bone lever system, the original sound wave wouldn't have enough force to continue. Its energy would simply bounce off the denser tissue of the inner ear and fade to nothing. Looking at this model of the inner ear, we see the final bone in that chain, the stirrup. It physically punches against the entrance to a coiled structure called the cochlea. This creates another massive shift in the medium. The kinetic energy leaves the solid bone and enters the fluid-filled spirals of the cochlea, generating tiny rolling liquid waves. Lining the inside of the cochlea are thousands of microscopic hair cells. As fluid waves wash over them, these tiny hairs sway back and forth, acting as a highly delicate biological microphone. When these hairs bend past a specific threshold, they trigger a chemical reaction that converts their mechanical swaying into a burst of electrical nerve impulses. At this exact microscopic threshold, the physical chain reaction of moving matter finally stops. The mechanical wave dies, replaced entirely by pure, actionable biological data. Returning to the cross-section, you can trace that data pathway along the green auditory nerve, which carries the freshly generated electrical impulses directly out of the inner ear. Those signals shoot up through the neural pathways and finally arrive in the dark, silent vault of the brain, specifically the auditory cortex. Here, the brain rapidly decodes raw electrical voltage into the rich, subjective experience of pitch, tone, and volume. The psychological warmth of hearing a familiar voice is actually the final translation of invisible, colliding air particles that started entirely outside of your body. Interestingly, engineers have reverse-engineered this physical process to build specialized tracking technologies. One prominent method is ultrasound identification, or USID, an indoor positioning system that tracks objects using high-frequency sound waves. As detailed in this schematic, USID relies on small tags that emit ultrasonic signals, frequencies well beyond what our biological ears detect. A network of sensors receives those bouncing signals, measuring the exact timing and distance to pinpoint the tag device's location. From a human ear detecting a friend across a room to an automated system tracking inventory, The principle is the same. The mechanical ripples of the physical world are being captured and decoded.